we have the pleasure now to introduce the last talk by Maurício Richartz, like we say in Brazil. I hope I'm pronouncing well your name, Maurício. And he'll talk about the introduction to black hole perturbation theory. So it's your turn now, Maurício.
Thank you, Paulo. I believe you can see my slides, right?
Yeah.
And you can hear me. And so let's continue. First, just to inform you everyone that I have compiled all 3 lectures, including today's lecture, and all the notebooks in just single files. So I think Giuseppe just sent me an email saying that they are already on the website. I have also put them in my website in case it wouldn't be online already, but so you can go to the website of the school and you see them there. Another important thing is that there was the third part, where I was going to talk about a little bit about the Radial formalism and the Newman-Penrose formalism, but unfortunately we won't have time for that. Probably in the last 5 or 10 minutes, I'll speak a little bit about the Newman-Penrose formalism and explain how it connects with everything we've done here in this last 2 lectures and today. But I won't be able to do any detailed analysis, and I've not prepared any slides about that. Okay, so let's go back to where we stopped on Tuesday, and we were talking about the methods. So in the first lecture on Monday, I explained to you about the Klein-Gordon equation in Schwarzschild and Kerr backgrounds, how you can separate the equations and what you can do with them. And so we saw a little bit about the scattering problem. We defined the superradiant scattering and the quasi-normal modes and quasi-bound states. And then in the second lecture on Tuesday, we started with the numerical methods, and we saw basically how to implement the continued fraction method to determine the eigenvalues of a differential equation. And in particular, we used that to find the eigenvalues of the angular equation for the scalar field around a rotating black hole, curved black hole. And now we will keep going, and we will use this basically the continued fraction method to find quasi-normal modes and quasi-bound states. And we will also solve the scattering problem in the frequency domain and the time domain. So this is what we saw on Tuesday, and now we're back to the scattering problem. Let me just go back here a few slides. So here, just again to remind you the picture of the scattering problem. We have the radial equation here, number 39, and the angular equation, number 40. The angular equation is the spheroidal, the equation for the spheroidal harmonics after we impose the regularity boundary conditions at the poles. So chi equals -1 and chi equals +1. And the radial equation, you also need to impose boundary conditions, and basically the physical boundary condition we want to put here is that at the horizon there is only the ingoing wave. We don't have any outgoing modes, and so this translates into this picture here where we only have the ingoing wave characterized by this amplitude AI. And here this is the picture for the Schwarzschild case, where we don't have background rotation, so we don't have a spinning black hole. Otherwise, we'll see that it's slightly different. And so basically, we do as we did in the first lecture. So we'll start here. This is the radial equation, and we studied in the asymptotic limits first, so far away from the black hole, when the tortoise coordinate goes to plus infinity, and near the horizon, when the tortoise coordinate goes to minus infinity. So at minus infinity, as I said before, we only have the ingoing wave, and far away, we have both ingoing and outgoing waves, so the incident and the reflected wave. And here the quantities we defined before. So omega tilde is this effective wave number that shows up here, and it basically depends on the azimuthal number m of the wave and on the angular rotation of the black hole. And this angular velocity of the black hole is given by this term here. Sorry, this m shouldn't be in here, it's already in here, so there's no m here, it's just a divided by 2 capital M r plus. R plus is the event horizon, and k is the wave number for locally for the waves far away from the black hole, and it's basically the square root of omega squared, the frequency of the wave, minus mu squared, the mass of the scalar field. And as we saw, I think on Tuesday, so you can start it as radial equation. You can write it as a Schrödinger-like equation, and that's how you reach this asymptotic behavior, which is shown here in equation 50. But in order to avoid having to deal with this inversion between the tortoise coordinate and the regional coordinate, I prefer to use the regional coordinates, capital R and small r. The disadvantage is that you lose this simple interpretation in terms of the Schrödinger equation. But if you already know what is the ingoing wave, what is the outgoing wave, then you can just go back to the original coordinates and do the calculations there. And there's no problem in doing that. So that's what we do. So here in equation 50, we have the asymptotic behavior in the tortoise coordinates using this psi function here. So if we go back to the capital R function and the little r coordinate, we can rewrite those the asymptotic behavior basically this way. For simplicity here, I'm assuming that the scalar field mass is 0, but you could basically repeat everything without assuming this. It just makes the notation the simpler, since some terms will be 0 because of this. But the idea is exactly the same, even if the mass is not 0. We only have to remember that since we are studying scattering problems, we want the frequency omega to be bigger than the scalar field mass. So if the scalar field mass is 0, then there's no extra restriction. But if it's not 0, then the frequency should be bigger than this scalar field mass. So basically, in terms of this coordinates, we get this behavior, and we want to solve the equation, the radial equation, and using initial conditions that are compatible with this asymptotic behavior here. So we have here 3 observations. So the first thing is that the equation is linear. So the differential equation is linear. So if you have a solution and multiply by a constant, you obtain another solution. So basically, the first thing we can do is divide everything by this coefficient here, yt. So yt, yi, and yo are constants. So T stands for transmitted, I for incident, and O for outgoing. I for ingoing and O for outgoing. So this is the incident wave, the YO is the amplitude related to the amplitude of the reflected wave, and YT is related to the amplitude of the transmitted wave. So the first thing you can do is you can divide the equation by a constant and you still get another solution. It's still a solution. So you divide everything by YT, and effectively what you're doing is you're setting YT to be 1. So then if you do this, you basically know what is the behavior of your function near the event horizon. And so you know the function, so you know the function at a point near the horizon, and you know the derivative of the function. So this is basically what you use as initial conditions for your for solving your ordinary differential equation. In these coordinates, since the horizon is a singular point, you can't actually start exactly at the horizon. Otherwise, you get divergences and strange behaviors, and your code will not work. Your numerical procedure will break up. So you have to start an epsilon away from the horizon. So we actually, when doing the calculations, we impose the boundary condition an epsilon away from the event horizon. So that's what I'm saying here. So we impose basically, we basically calculate this behavior, this function here. We substitute here r equals r plus epsilon, then we get epsilon to the power of minus I sigma, and sigma is known since we know the mass where the event horizon is. R minus is the Cauchy horizon, and so it's another root of that delta function we've seen on Tuesday. And omega t is also known if you have given the frequency, if you have chosen the frequency. So we know everything, and we then have the initial condition. We then solve the equation. We start then near the horizon, and we evolve the equation, solve it until a point which should be sufficiently far away from the event horizon. Since we can't actually go to infinity when doing numerical calculations, so we should stop very far away from the horizon. So then it depends where to stop, depends on how much precision you want. But typically 100 times the location of the horizon is more than enough for what you're doing. And there are other ways to improve this without actually increasing your domain. You can basically put more right corrections to this asymptotic behavior, which make your extraction more accurate far away from the black hole. So just keep in mind that this R1 should be a point that represents infinity in our numerical calculations. But since we can't go to infinity, we just choose a point that is sufficiently far away from the horizon. So basically, we solve that equation, starting from the event horizon. We then find what the function R and its derivative, the function R and its derivative, what are their values at this point R1 far away, and then if you know the function and the derivative, you can then find what is this coefficient here, yi and yo, and from then you can then calculate the reflection coefficient, which is basically yo divided by yi squared, the absolute value squared. And here we have the result of this implemented in Mathematica. I'm going to show you the implementation in a second. Let me just explain the plot a little bit. we have here on the horizontal axis, the frequency, omega, divided by this quantity here, m capital omega. And remember that on Tuesday, we've seen that superradiant scattering, that is extraction of energy from the black hole, happens when the frequency is sufficiently small. And the condition was that the frequency omega should be smaller than this quantity little m capital omega. So when this ratio here is smaller than 1, we find superradiance. And mathematically, so superradiance translates into the reflection coefficient being greater than 1. So the amplitude of the reflected wave is larger than the amplitude of the ingoing wave. The flux of energy going outside, going away, is larger than the energy flux going into the system. And here we plot this reflection coefficient, so as a function of this ratio here, for different spin values. So we start here at 0.8 and stop at 0.999. Remember that the maximum here is A equals 1. And here I'm assuming that the mass of the black hole is capital M equal 1. So I'm normalizing everything by the mass of the black hole. So M equals 1 means that the maximum spin that we can have is 1 as well. If we go past 1, so if A is 1.5, for instance, then we don't have a black hole anymore. Then it's a naked singularity. And you can see here that, take for instance 0.8, the spin is 0.8, and you can see that the reflection coefficient starts at 1. So for very small frequencies, very small frequencies, everything that goes in gets back, so it's reflected. And but as you increase the frequency, this reflection coefficient starts increasing, and then it reaches a maximum, and then it starts decreasing again. And here the plot stops, but if you keep going, you see that it crosses r equals 1, and then it goes to numbers that are smaller than 1. So for very high frequencies, your reflection coefficient tends to be 0, and that's natural, like very, it's easy to get an intuition for that, because if your frequency is very high, then your energy is much higher than your potential, effective potential barrier. So it's easy to go through the potential barrier since the energy is much higher than the top of the potential. So everything should be transmitted. And if the frequency is small, then everything should be reflected. And you can see, so for this small but not very small frequencies, you get these amplifications, which become higher and higher as you increase the spin of the black hole. But they don't keep increasing until you reach A equal 1. They increase and they reach a maximum, they get this peak, but then the peak starts decreasing if you keep increasing A. So the maximum here is for A 0.99, but I mean, you can do it in a more detailed calculation, and you find, I think it's 0.98 something. I don't recall the correct number where you get the highest amplification. And the highest amplification you can see here is it's around a bit more than 1.003. So I think the maximum you can get is 0.38% or something like that for a scalar field. You could do the same.
Sorry, João Paulo has a question, maybe.
Sure.
Hi. Can you explain more about the limit where A goes to 1? Because here we have A equals to 0.99939.
Right.
So what's happened when you increase the values of A, or I don't know, take the values to be 1?
Right. So let me go back a little bit here. I think I have to go to the very beginning. Yes. So So here's the Kerr metric, right? And you have this delta function here, which basically appears here in the RR term of the metric, GRR term. And you can see that when delta goes to 0, then this coefficient here diverges. So the metric diverges. And you can then study if this is a singular point or if it's just a singular. This happens only at the problem is with the coordinates you have chosen, and you can show, as in the Schwarzschild case, that when delta is equal to 0, you don't have an actual singularity of the space-time. It's just a coordinate singularity, and you can see that delta goes to 0. So the points where delta goes to 0 are the roots of this second order polynomial here, r squared minus 2m r plus a squared. You can see, so this is if you plot this, you get a parabola, right? And this parabola has is open upside, so you can work out and see when you have real or complex roots. And you see that you have complex roots when the mass is smaller than this parameter A, when m is smaller than the spin of the black hole. So when A is larger than m, then you don't have a black hole anymore, right? When A is equal to m, then it's the case of an extremal black hole. So this is called an extremal black hole because the two roots of the delta function coincide, so that they merge. So now we understand that when A is larger than n, then you don't get a black hole anymore. So the problem is that then, since you don't have a black hole anymore, we don't have the event horizon anymore. So we don't know, I mean, there's no reason why to impose this boundary condition anymore of only ingoing waves at the horizon, since we don't have the horizon anymore. Let me go back here. Yeah, here's fine. So we don't have the event horizon anymore, so there's no reason to impose a boundary condition like that now. So that's why it doesn't make sense to do this for A equals bigger than 1. Of course, you could do something similar, but then you need to impose a boundary condition, and there's no natural or physical way to do that. Especially since you don't know what happens at singularity. You could have something coming out of the singularity, and at A equals 1, you could just solve the equation again. There's no problem. It's harder to calculate the quasi-normal modes for the extremal case when A equals to m, so A equals 1. Because the singular points of the differential equation are different, so there's a confluency there, and the horizon becomes an extremal, an irregular singular point. So the details become more complicated. But for the scattering case, for this problem, you could just calculate for A equal 1. It should work as well. But I haven't done it here, I guess, because I'm used to only going close to the extreme limit, but not going exactly at it. I guess I answered your question, but let me know if you have any. Okay.
Thank you.
So that's it. I guess you can see my notebook now. Let me know if you can't. And so here now, all of those things I was talking about yesterday, on Monday and Tuesday are here only in this whole in this notebook. So the first two parts are the basics of the Schwarzschild and the Kerr metric, separation of variables, and so on for the scalar wave. The eigenvalues, the eigenvalues of the angular equation we did on Tuesday are here. So now we are doing the scattering. Let me increase it so that you can see it better. I mean, you have access to this notebook, and so if you have Mathematica, you can play around, and I'm just defining here the quantities. Epsilon, XP is the horizon. It should be well commented so that you can understand what is being done here. But if you don't, you can just send me an email. I'll try to explain, or you can ask me now or during the discussion session. And basically the definitions of the parameters here, the differential equation. We could calculate the spheroid eigenvalues using the continued fraction method, but since Mathematica already has it, we can use it too. So I'm using Mathematica's native function for the eigenvalues. Here I'm defining the initial conditions. So based on the asymptotic behavior near the horizon, we have here the function and the derivative of the function. So I define it here. And here is just, I'm using the Mathematica's ND-solve function. You could implement it by yourself by doing like discretization of the space-time of the space and then evolving. But here to make it simpler, I'm just using ND-solve. And then after you solve the equation, you have to extract the coefficients to get the reflection coefficient. So here we extract it. So after this, we find this y in and y out. So that the amplitudes of the ingoing and the outgoing wave. And here just the procedure to basically calculate the reflection coefficient based on the solutions on the differential equation. So here I just make a table frequency by reflection coefficient, and so you run it for different values of A here, 0.999, 0.99, and I plot everything together. And here the plot with all the definitions. And I'm using here this package Matex, so it's pretty easy to install. You can just go to this website. There's you can install with just one single command in Mathematica. If you have Mathematica 11 or 12, I guess it works. It's just one command. It's explained here. It's just for the latex notation, but if you don't want it, you can just plot it directly in Mathematica, and then you get something like this. You can also put right the legends here as well, but well, anyway, let me go back now to, okay. So this is all for superradiance, for the scattering in the frequency domain. So after you separate the variables, now let's talk a little bit about the quasi-normal modes. And for the quasi-normal modes, we can do basically the same thing we did for for the angular eigenvalues. We can do with the radial eigenvalues. So we started the radial equation, and then we, differently from the scattering problem, we now want to impose an extra boundary condition at infinity. So if you're studying quasi-normal modes, you don't want outgoing waves at infinity. You only want ingoing waves. And so you can do this by plugging in these ansatz here, which is equation 52. And this ansatz here already has naturally both boundary conditions at the horizon and at infinity. So at the horizon, it is an ingoing wave, and at infinity, it's just an outgoing wave. Sorry, it should be plus here, IKR. because at infinity you don't want, you just have the outgoing wave. I'll make the corrections later. So this should be plus IKR, but it's just a typo. Everything in the notebook there it's correct. And so if you plug these ansatz into the differential equation up here, yeah, sorry, there's also the coefficients here are missing. There should be the sum of Bn times this factors here. So there's a coefficient Bn here missing. I'm also gonna correct that. So if you plug this ansatz into the differential equation, then you get a 3-term recurrence relation for this coefficients Bn, which should be in here. And this is basically the same as in the case of the angular equation. The only difference, of course, is that the coefficients alpha, beta, and gamma that show up in this recurrence relation are different than before, but the idea is the same. Just one quick quick comment. When you make this expansion here, so you see the outgoing behavior, there's this R minus R minus, so R minus R is the Cauchy horizon, and you could do the expansion without this term here, but then you would instead of a 3-term recurrence relation, you probably would get more terms, so 4 or 5, I think, and then you would need to reduce the 5-term recurrence relation to a 3-term recurrence relation. There are some techniques to do that, but in this case, it's simpler just to start with the 3-term recurrence relation. It makes everything much easier to work with. Another important detail is that here I'm making the sum over this whole thing here, R minus R plus divided by R minus R minus. So this new coordinate here, and we do that because when you make this, you use these variables, basically you can guarantee that the sum is convergent everywhere from the horizon up to infinity, except possibly at infinity, when R goes to infinity. And to guarantee that it converges also at infinity, then you have to impose the continued fraction equation, which is basically this one. So if you solve this equation, remember this equation is an infinite continued fraction. It depends on these coefficients beta, alpha, and gamma, which show up in the recurrence relation. But if you solve this equation and guarantee that it is satisfied, then you guarantee that the sum is convergent everywhere for all values of R, starting at the horizon and up to infinity. Sorry. When you do it numerically, of course, you can sum infinite terms, so you have to truncate this at some point, as I explained to you on Tuesday. And we can do it in mathematics as we did before. But I think it was Rodrigo who asked on Tuesday what we do if we have 2 equations. So we have the equation for the radial eigenvalues, the equation for the angular part, and we have in the end 2 eigenvalues, and they show up in both equations. So these coefficients alpha, beta, and gamma, they depend on both the eigenfrequency omega and in the eigenvalue A. And the same is true for the equation for the angular part. It also depends on the frequency omega and the eigenvalue A. And then, sorry, and then, but you can solve both equations simultaneously, and we then get something like this. So here, I'm also going to show you the notebook in a second, but what I'm doing here is I'm finding the eigenvalues when here, just for simplicity again, I'm assuming that the scalar field has 0 mass, but you could do the same without this assumption. L and M are equals to 1, and they are the azimuthal wave number and the orbital wave number. And we basically here change the value of A and compute the real part of the frequency and the imaginary part of the frequency. And I'm plotting here just to show you that just an example how it changes as the spin increase. So here we have Schwarzschild, A over M equals 0. And then as you increase the spin in this, for this quasi-normal modes, the real frequency, so the real part of the frequency, the oscillation frequency increases, so it's oscillating faster as the spin increases, and the imaginary part also increases, so it goes to minus 0.1 more or less to minus 0.05, so it's getting closer to 0. So it becomes more stable, it decays slower if you increase the spin. So, and note here that these modes we find are always stable. They have the imaginary part always smaller than 0. And there are some rigorous proofs that this is always the case when you have a scalar field around Kerr, a massless scalar field around Kerr, all quasi-normal modes. You only find these modes that have the negative imaginary part. You don't have instabilities in this case. Let me keep going and show you the quasi-bound states, and then I'll show the notebook for both together. So basically, we can also study, instead of quasi-normal modes, quasi-bound states. Remember that the difference here is that at infinity, you impose an extra boundary condition, and that this boundary condition is of purely exponential decaying modes. You don't want exponentially growing modes far away, and typically they are associated with a well in your potential, in your effective potential. So there's a well where you can confine the modes, so they are trapped inside a potential well, and they can only happen when the mass of the scalar field is not 0. And so they also occur in Schwarzschild. But for Kerr black holes, which we are studying here, there's a nice or interesting curious behavior, which is that these quasi-bound states can be associated with instabilities. So here we plot these quasi-bound states, which we find by doing exactly the same procedure that we do to find quasi-normal modes. We use the continued fraction equation. And I'm going to show you it in how we do it in the notebook. But in the end, I'm changing here. I'm fixing now the spin of the black hole, 0.95, and the orbital and azimuthal number are also fixed. And we increase the mass of the scalar field and see what happens to these quasi-bound states. As we can see here, we have the real part and the imaginary part. So, sorry, the imaginary part here on the left and the real part on the right are the quasi-bound states of the frequency of the quasi-bound states. And you can see in this plot, there's nothing very interesting going on. Just the imaginary, the real frequency, so the oscillation frequency is increasing as you increase the mass of the scalar field. There's more interesting things you can see about this plot, but they're going to come in the next slide. Here, what is interesting is the imaginary part, which tells you if the mode is decaying or increasing in time. And you see that if the mass of the scalar field is sufficiently small, so here when it's, let's see, around 0.37, so smaller than 0.37, you have imaginary parts which are positive. So this means that the waves are growing with time. So these are unstable modes. there's this peak here, so it goes to 0 and the mass goes to 0, and then it starts increasing as the mass increases. It reaches a maximum instability rate, and then it decreases and then becomes stable after 0.37. This is for 8.95, but if you use a different A, then you get the peak and the transition from instability to stability at different points, but it also basically the same thing happens. Another interesting thing is, besides that, this maximum instability here, you also have a point where, so we have this transition from instability to stability, which here happens at around 0.37. So if you are exactly at this 0.37, more or less, where the imaginary part is exactly 0, so 0.37 here, you find that you have a real frequency also around 0.36, 37. And so at this point where the imaginary part of the frequency is 0, you have a stationary mode. So people usually call it a stationary cloud. So it's a scalar field that is living outside your black hole, and it's there forever. It won't never decay in time, and it won't grow in time. So it stay there forever without growing and without decaying. So this analysis at the linear level, right? So we are just studying a perturbation around a black hole, and the black hole and the background is fixed. But people realized, I think the first analysis still in the linear level was in 2012 or something like that by Hod, and then some people, Carlos Herrero and a collaborator, they studied the problem in a nonlinear setting, so solving the actual Einstein equations coupled to a Klein-Gordon field, and they found that you can find solutions which are basically analogous to this stationary cloud around the Kerr black hole. So these are called these black holes with scalar hair that people talk about now, and there's a lot of research going on recently about this black holes with scalar hair. This doesn't violate the no hair condition, because usually for the no hair theorems, you have to assume that your field is static, but here they're stationary. So it was actually a surprise when people, well, not a complete surprise, since there were already this analysis for in the stationary case in the linear level, but it was still quite interesting to find this nonlinear solutions. So the solutions to the Einstein equations coupled to the Klein-Gordon equation that are related to this stationary solutions here. But anyway, so just to conclude this part here about the quasi-bound states, we can look at the real frequency, and we can compare it with the condition for superradiance, and we can compare it with the mass of the scalar field, and that's what I do here. So on the left plot, I show you the ratio between the real frequency and the scalar field mass. And you see that for all these modes, so these plots here correspond to exactly the same situation as this. And you can see that these modes, they have this ratio here, the real frequency divided by the scalar field mass, is always smaller than 1. So this is very characteristic of these quasi-bound states. This means that your energy is very close to the value of the potential at infinity, which is just mu, the scalar field mass, but it's slightly below. So what it means is that you're basically in a region where you trap your modes inside the potential well that is formed in your system. For quasi-normal modes, you typically have this number much larger than 1, this ratio here. But for quasi-bound states, it's very close to 1, but it's smaller than 1, this ratio. You can also compare the real frequency with this number here, m capital omega. Remember that this was the when the frequency is real, this ratio here tells you if you're satisfying the superradiance condition or not. So if this ratio is smaller than 1, then you're inside the superradiant regime. And if it's bigger than 1, then you're outside the superradiant regime. So just to remind you, it's this plot here. So here we are always in the superradiant regime because this ratio is smaller than 1, and you have the reflection coefficient greater than 1. But if this becomes bigger than 1, then you don't have superradiance anymore, and that's what we are seeing here. The superradiant modes, so when this is smaller than 1, stop here at 0.37, and starting from 0.37, then you have the non-superradiant modes. But if you recall, 0.37 was exactly the point where you have this transition here from instability to stability. So it's not a coincidence. So all these unstable modes are related to superradiant. So they happen when you trap. Intuitively, you can understand as superradiant modes that are trapped inside the potential well. So they keep going back and forth inside the potential well, basically, if you think that it's propagating in some way. And so basically you keep amplifying, self-amplifying the initial mode, and then it becomes unstable. So this is just intuitively way to understand, but not very rigorous what I'm saying, but it's a good way to understand what's going on. And let me see what else. Oh, so when the superradiant condition is exactly satisfied, so when this is 1, so basically at 0.37, where you have the transition, you can see that the effective frequency, so if you go back to the scattering problem, this effective frequency becomes 0 in that case, at least the real part becomes 0. And then this means that this exponent here is 0. But if you can study the energy flux of the field, the scalar field near the black hole, and you see that when this superradiant condition is exactly satisfied, so when this term is 0, then you have a 0 flux of energy through the horizon. So it's natural, it's not a surprise that when you have a 0 flux of energy through the horizon, then you get these stationary clouds. So these modes here with 0 imaginary frequency, which don't grow and don't decay in time. So it's very natural that they correspond to a 0 flux of energy through the horizon. So you're not losing energy through the horizon, not extracting energy from the horizon, from the black hole. All right, so just very quickly, maybe you can see it now, but this is in these other notebooks here, these other sections here of the notebook. So the scattering problem was what we just talked about, and then you have the radial eigenvalues. So in this one, it's again commented a lot of commentaries in the notebook. So basically what we do here is we make the separation. We perform the continued fraction algebra. So we plug in the n sets and find the recurrence relations. So in the end, we find just the alpha, gamma, beta, and alpha coefficients. And then using these coefficients here, we calculate the quasi-normal modes. And this is basically the same that I showed to you on Tuesday when we did it for the angular eigenvalues. Here we do for the angular and the radial eigenvalues at the same time, since the equations are mixed together. And then here we do the same for the quasi-bound states. So just define the alpha, beta, and gamma coefficients, and solve the continued fraction equation. And here, just the results, the same plots I showed you before in the slides are here. So you can, it's all commented, and if you have time then to look into detail and have doubts about it, just send me an email and I'll try to explain if there's something that is not some doubt that remains. And finally, the last part here, the scattering problem in the time domain. So the idea here is, so now we go back a little bit, we go back to the scattering problem, and let me show you this picture again. So here we, as I mentioned on Tuesday, we think of the process as being completely stationary, right? So it's happening all the time, and it's just oscillating with this frequency omega, but at any time when you look into the problem, you see this behavior here: an ingoing wave here, ingoing wave here far away, outgoing wave here far away. So
sorry,
there's
Maurício,
a constant flux.
I think you still show in mathematical file.
Oh, now I think you should be seeing it, right?
Right.
Okay, sorry about that. So here in the scattering problem, we have an ingoing flux, constant ingoing flux to the horizon, out far away, constant ingoing flux, constant outgoing flux, and at all times it's always like that. But you can study the problem in the scattering domain. Sorry, in the time domain. So in the time domain, the idea is to write an initial wave like a pulse, and then you send the pulse towards the black hole, and then it scatters off, and then after time goes by, there's no wave anymore, everything has passed, and so it's in some sense more dynamical, I would say. So the difference is that here you don't separate into modes, right? So basically, you can't translate one problem to another, of course, if you like expand into modes and so on, and then you find the expansion coefficients. So basically, if you do this Fourier transforms and so on, but we can directly solve it in the time domain. For a Kerr black hole, it's more complicated because you can't separate the angular values as well. You have to include the phi component here. You can't separate in the time domain the equations. You can only separate the equations in the frequency domain. So the angular part included. But for the Schwarzschild case, you can separate as before. So I'll just stick with the Schwarzschild case since it's simpler. I'm following here this reference, the ideas in this reference by Gunlach, Price, and Pulling. And as before, we separate the angular parts as using the spherical harmonics, and the time and radial components will basically satisfy this differential equation here, equation 55, which is the same we saw on Monday. And the idea here is to use a different coordinates. So we use the light cone coordinates U and V. So U is the retarded time, T minus R star. V is the advanced time, T plus R star. And if you use these coordinates, then the equation assumes this simple form, 56. So you just have the mixed differentials for the mixed partial derivatives, and then the potential. And the idea is to discretize this equation, and then solve it subject to some initial data that you impose. And typically people assume that a Gaussian profile for this initial data. So the idea is that you discretize the space and time now, but space and time now are in terms of this coordinates u and v. So you have this grid here, and then you impose your initial data. So you specify your initial data at these lines here, u equals 0 and v equals 0. So at this, basically at the axis here, at the semi-axis here, you impose your initial data. So basically at all the grid points, you know, on the axis, at least, you know what the function is. Then you discretize the equation. So you use a finite difference rule for substituting your derivatives. So this equation 56 becomes this equation here. Here N, W, E, and S are points on the grid, and you can see what they represent here. So W, N, E, and S. I guess I'm running out of time, but it's just 2 more slides after that. It should be quick. Basically, what this equation here is telling you is that you can determine what the function psi, so the scalar field at the point N is based if you know what the function is on W, S, and E. And you also need to know the potential V at the point S. So S for south, N for north, west, and east, right? So you know what's happening in the north if you know what's happening in the west, east, and south points. And then you do it recursively. So start with your initial data. So you know at this, you know at this point what the function is, at this point and this point. These are just the initial data. And then you apply this equation and you find what it is at this point here. And then you know now what it is in here, you know here and here because of initial data, then you find what it is in here. So you keep going and you find it here, find it here, find it here, find it here, find it here. Then you go to the next line. So you know what the function is here, here, and here. Then you find it here. I guess I hope you can see my mouse, otherwise I'm just, it will be hard to say, to understand what I'm saying. But then, so if you know it here, here, and here, then you find it here, up here, and so on. So then you keep going up on the lines, and then you, in the end, you find the function at all grid points. This is done in the coordinates u and v, but you can go back to the original t and r star coordinates. And if you do that, then you can evolve initial data. And here's an example of that I did in Mathematica. So at some initial time or very earlier time, you have just the pulse here. This is going to the left. This is going left, and the horizon, remember, is at -infinity. So this is going left. You can't tell just by the figure if it's going left or not, but I'm going to show you the movie. So this pulse is going left. Then it interacts with the black hole. The potential is basically at r equals 0. So this is more or less where the peak of the potential is. So it's very close to where the peak is. Then it interacts, and then at some later time, here it's 70 in dimensionless units. You have this outgoing wave now, the reflected wave, which is going to the right, and the transmitted wave, which is going left. And you can actually compute reflection and transmission coefficients here. If you integrate basically this waveform on this side, and then you integrate this part, and you use the flux of the Klein-Gordon field using the energy tensor, the Starr's energy tensor, and then you do the same for this, and then you compare this energy fluxes, and then you should coincide with the reflection coefficient. Well, not coincide because here you don't have a single defined frequency, but if you have your peak concentrated, in a way that is related to a pulse width of very in the frequency domain. This would correspond to something that is has a small spread around a single frequency. Then you should translate this into the results here should translate to the reflection coefficients in the frequency domain analysis, or should be similar. And you can also see the quasi-normal modes by doing this analysis. So if you fix the here I'm fixing time in each case and plotting the field as a function of the coordinate r. You can do differently. You can fix the coordinate r and plot the field as a function of time, and then you get something like this. And here is the amplitude, the absolute value of the field as a function of t, and I'm using a logarithmic scale here. And you can see here three characteristic phases of this behavior. So the initial part here, I would say around up to 60, you have the initial perturbation. So this is the initial pulse that is sent and that is interacting and showing up here. And then after the initial pulse passes, you see the relaxation of the field, which is basically these oscillations here that are decaying. If you join the peaks here, it should more or less look like a line. So a linear decay here. Since it's a logarithm scale, it's an exponential decay in time. So these are the quasi-normal modes. And if you basically find a line here and then calculate the angular coefficient, it should match the values found in using the continued fraction method in the angular in the frequency domain. At least that the most stable, the fundamental mode should be this one. And then you have this final phase here, which is the so-called late time tail, where the behavior of the field is not exponential anymore. It's decaying now polynomially in time. So it's a polynomial. And people also study that a lot. And that's it. I think I ran out of time, but there's a notebook in Mathematica where I'll also calculate that. And I guess I can keep sharing it. And so I'll end up here. I was going to talk a little bit about the Newman Penrose formalism, but this will be for another time. Thank you.
So, thanks a lot, Maurício. Let's thank Maurício for the nice mini course.